If you've studied statistics at any point, then there's a good chance you've heard about what could be the longest standing beef in statistics, the one between the Frequentists and the Bayesians. It's not a bloody conflict, these are statisticians we're talking about, but rather it's a philosophical one. In my last video on this topic, I focused on talking about the Bayesian side of things since most people are taught Frequentist methods. In this video, I wanted to take a step back and shed some light on the heart of this conflict and tell you whether or not it's something you actually need to worry about. Maybe you're a dedicated Bayesian, or maybe you're a hardcore Frequentist for some reason. Most likely, you're just someone who's curious to know a little bit more, and you've come to the right place. If you're new here, thanks for tuning in. My name's Christian, and this is Very Normal, a channel for making you better at statistics. Let's get into it. We'll start with a simple question. What is probability to you? Probability is one of those things that feels intuitive at first, but once you really start to think about it, you'll realize it's pretty complicated. Complicated enough that people have argued about it for hundreds of years. Both the Frequentists and the Bayesians have their own particular definition of probability, and it's from these opposing views that led to different approaches to statistics. So before we see how these different schools of thought produce different or not so different analyses, we have to talk about probability. The so-called classical definition of probability is something most of us have been taught in school. Classically, the probability of some event A is defined as the proportion of the number of ways A can happen and the number of possible outcomes. According to the classical definition, calculating probability comes down to simple counting. Examples that come with this calculation often deal with gambling, including coins, dice, and playing cards. It's relatively easy to count the number of ways things can happen with these types of simple experiments. The classical definition of probability is intuitive and straightforward to calculate, but it's only intuitive and straightforward for simple types of experiments like the ones I've described. When you start to explore more complex types of events, it might not be so clear how to do the counting you need. But the idea of probability as proportion or frequency was here to stay. In fact, the idea was so appealing that some people have just started to say that frequency was probability, full stop. This is known as the Frequentist interpretation of probability. According to the Frequentists, you could calculate the probability of an event through repeated experiments instead of having to count like in the classical definition. The typical example is a coin. You assume that there's some fixed but unknown probability of the coin landing heads. To calculate this probability, all you need to do is flip this coin a large number of times and calculate the proportion of flips that land heads. Each of these individual flips are considered to be independent and are referred to as experiments, since each one produces a data point. And there's solid math that goes behind this idea. We have a theorem called the law of large numbers, which states that the proportion of heads will get very close to the true but unknown probability as the number of flips approaches infinity. That is, Frequentists interpret this so-called long-run frequency of heads as the probability of getting heads, because you can make them arbitrarily close. This idea is powerful because theoretically, it could be applied to all sorts of situations beyond coins, dice, and cards. For example, we might want to calculate the probability that someone will develop a rare disease. The idea is that you look at many people who are assumed to come from the same population, see how many of them develop the disease, and use the proportion of people who get sick to represent the probability you want. The law of large numbers is an essential theorem in statistics. But if you think about it a little further, it also raises a lot of questions. First of all, how large does large have to be for the frequency to be close? Your first reflex might be to point at the theorem and say, well, as the number of people goes to infinity, you'll be arbitrarily close. That's not super helpful in a world that only produces finite datasets. Next, the law of large numbers only tells you that the observed frequency will be close to the true probability, not what it actually is. Being close is fine for practical purposes, but if frequentists insist that frequency is probability, then it's somewhat troubling if the thing you're using to represent it can only ever be close and not exact. And finally, there are a lot of situations where the Frequentist definition just doesn't apply. Past events, rare events, and one-time events are all incompatible with the Frequentist definition because the notion of repeated experiments doesn't apply here. This brings us to the Bayesian interpretation of probability. To understand the Bayesian perspective, we need to take a look at Bayes' rule. According to Bayes' rule, the probability that an event A will happen conditioned on another event B is the product of the marginal probability of A multiplied by the conditional of B on A divided by the probability of B happening. Bayes' rule describes the calculation you need to make to update your probability that A will happen after you see B happen. This marginal probability is interpreted as your personal belief that A will happen before seeing B happen. That is to say, probability in Bayesian terms is subjective. Another way to interpret Bayesian probability is that it's a degree of belief that an event will happen, measured on a numerical scale from 0 to 100. Once we see B happen, Bayes' rule tells us how to update this belief number. If you've only thought of probability as frequency up until now, this new subjective interpretation can be difficult to accept. But I'd argue it's actually more in line with what we do every day. We update our beliefs all the time as we gather new information. We just might not assign a specific number to it. When you're watching a movie, you might try to predict what will happen next as you see the plot unfold. That's Bayes' rule in action. You might feel a pit in your stomach if your significant other tells you that you need to talk. That's Bayes' rule in action. And now you may have noticed a progress bar start at the bottom of the screen. And thanks to your natural Bayesian ability, you should have a pretty strong belief that this video was sponsored by Brilliant. Brilliant is an online platform that has over 70 interactive courses in various fields, including math, computer science, and programming. One of the best parts of Brilliant is its focus on active learning. Instead of making you mindlessly read through text, Brilliant lets you take a hands-on approach with your learning with interactive exercises and quizzes. This way, you build a more intuitive understanding of the material that will serve you better in the real world. Brilliant has both basic and advanced material to accommodate people who are at different points in the learning journey. To try everything Brilliant has to offer for free for a full 30 days, visit brilliant.org/verynormal or click on the link in the description. You'll also get 20% off an annual premium subscription. Thank you Brilliant for sponsoring this video. Let's get back to probability. Probability as subjective degree of belief is nice because it's very flexible. Everyone can have their own probability. But an issue comes when you try to apply it to some common sense probability rules. One of these rules is that the probability of an event happening or not happening should equal 100%. Under the subjective definition, this axiom doesn't need to be respected. I could believe that an event A will happen with 20% probability and that it won't happen with 50% probability. This flexibility is a great advantage, but it also loses a lot of its mathematical rigor. After hearing these definitions, it's tempting but misleading to believe that the frequentist perspective is the hard, objective truth, while the Bayesian perspective is just soft, subjective feeling. I think that this view is too simplistic. The Bayesian definition of probability can be improved, and in fact, people have made great progress on this. One person who's made a lot of progress on this front is Edwin Jaynes, an American physicist. Jaynes viewed probability as merely an extension of logic, so his definition is often referred to as the logical interpretation of probability. To Jaynes, probability was still just numerical representation of plausibility or belief, similar to the Bayesian view, but he added some additional rules to force it to respect the usual probability axioms. One of these rules was that probability had to respect background information. Jaynes recognized that people rarely consider events purely in isolation. We will almost always refer to other information to judge if something is plausible or not. When your partner tells you, "we need to talk," your mind probably races to figure out all the different ways you might have messed up. Under the logical interpretation, probability cannot be divorced from someone's background information. A consequence of this is that there's no such thing as objective probability in an absolute sense. Background information can be represented in terms of conditional probabilities. Let's call X all of the relevant background information that someone has about an event. This background information can be other subjective beliefs, but it can also include other information like past data, research, or experiences. To be clear, X can denote multiple events or statements, but it's just cleaner to write a single variable here. With background information, the probability of any event A actually becomes a conditional probability. Jaynes's view of probability is compatible with Bayes' rule too. The only thing that changes is that all of the probabilities are now conditioned on background information. In this light, a prior probability is no different than any other probability. It's still your degree of belief about an event, but it's now conditioned on all the information that you have at that moment. The logical interpretation of probability helps to better define objectivity and subjectivity with probability. By conditioning on background information, it gives a better rationale for allowing two different people to assign different levels of plausibility to an event. Any differences come down to just having different background information. James's thought that if two people shared the exact same background information, then they should produce the same probabilities, thus bringing a more objective element to probability. So for the rest of the video, you can assume we're working with the logical interpretation of probability. If you're interested in learning more about this topic, then I highly recommend reading Bernoulli's Fallacy by Aubrey Clayton. This book formed much of the research for this video, but it goes much more in depth into the history and major figures in probability. I'll leave a link for it in the description below. Now that you know more about the frequentist and Bayesian interpretations of probability, you're ready to see how these interpretations influence how they apply statistical methods. But to do statistics, we need a motivating problem and a dataset. Something you may not know about me is that I really like coffee, and as a result, I like going to cafes with interesting forms of coffee. But when I plan to go to a cafe, I want to be pretty sure that I'll like what I get. To know if a place is good, I refer to their reviews. Let's say that I'm thinking of going to this place, Mostra Coffee. As I'm writing this script, these guys have 1,074 reviews and an average rating of 4.5 stars. I don't really trust 5-star reviews, so instead of using the star rating, I'll be doing a simpler analysis where I consider the 4 and 5-star reviews as evidence that the cafe is worth going to. My rule is that I'll consider going to a cafe if the probability they receive a 4 or 5-star review is more than 85%. I'm going to denote this probability of interest as pi. Now, I don't know what this probability is, but I can analyze the reviews to learn more about it. And I'm going to do the same analysis from both a frequentist and Bayesian perspective. What's important to notice here is the language I use to do these analyses, so keep that in mind. I'll start with the frequentist analysis. I'm examining the proportion of 4 and 5 stars for a single cafe, so this calls for a one-sample proportion test. My null hypothesis is that pi is equal to 85%, while my alternative is that it's not 85. I'll tolerate a type 1 error, aka level, of 5%, so my confidence level is 95%. Using the prop.test function in R, I can easily perform the test. Out of 1,074 reviews, there were 765 5-star reviews and 181 4-star reviews. This is all I need to run the test, so I can just go for it. The output tells me that the estimated proportion of 4 and 5-star reviews is 88%. The associated p-value is 0.0053, and the 95% confidence interval is between 85.9 and 89.9%. The p-value is less than my level, and the confidence interval doesn't include 85, therefore I reject the null hypothesis that Mostra Cafe's probability of getting a 4 or 5-star review is 85%. Based on what I said, can you tell where the frequentist ideas come into play here? First is my estimate for pi. Our estimate is literally a proportion, and from the frequentist perspective, it should be treated as close to the true value of pi. You can argue with the sample size of 1,074, it's really close, but it still doesn't really tell us what it is. Second is the use of level for the hypothesis test. I chose to tolerate a 5% level. This means that I tolerate a type 1 error with 5% probability. In this particular case, we rejected the null hypothesis, but if we were to repeat it multiple times, there's a small but controlled probability that this decision is wrong. But I want you to think about it a little further. What exactly does it mean to repeat the experiment here? To repeat the experiment with Mostra Coffee is to gather another 1,074 reviews, assume independence of the reviews, and see how many 4 and 5-star reviews we get in this new experiment. Based on the nature of the problem, this repeated experiments idea doesn't really apply here. Last is the confidence interval. Remember that confidence represents the frequentist probability that an interval covers the true value of pi, where all these intervals come from multiple repeated experiments. We run into a similar problem here as we did with the estimate. Notice that the confidence interval doesn't actually tell you if it contains the true value of pi or not. You can only know that if you repeated the experiment multiple times, then most of them will. Frequentist hypothesis testing requires us to imagine the repetition of the same experiment many times. Whether or not we can actually repeat it doesn't matter. We can always do it theoretically, or in non-technical terms, we can do it with our imagination. Now let's do the corresponding analysis from the Bayesian perspective. To set up the Bayesian analysis, I need two things. I need to decide what the likelihood of the data is, and I need to encode my beliefs and background information about the possible values of pi into a prior. For proportions like pi, we can use a convenient, simple model like the beta binomial model, where we assume the data to have a binomial likelihood, with pi as the parameter, and the prior on pi will be a beta distribution. The beta binomial model is a conjugate family, so I can skip the complicated computation of Bayes' rule and know that the posterior distribution is also a beta distribution with updated parameters that incorporate information from both the prior and the data. As for my own prior beliefs about how good Mosher's coffee will be, I'm not going to expect anything from this cafe, so from my perspective, the coffee is equally as likely to be good as it is bad. The way to do this with the beta distribution is to set both of the parameters equal to 1. Another way to describe this prior is uninformative. The true value of pi is still unknown, and the prior distribution reflects to what degree I think different values are likely and unlikely. You could easily change your prior by changing the values of the parameters for the prior. I'll show you an extreme example of this later after I work through this analysis. The number of successes in the data gets added to the first parameter of the prior, while the number of failures gets added to the second. So my resulting posterior distribution for pi is a beta distribution with parameters 947 and 129. You can think of the posterior distribution as a compromise between my prior and the likelihood of the data, so it's going to look something like this. You can see it's highly concentrated around 88%, and it looks somewhat bell-shaped. In Bayesian analysis, we derive a few quantities from this posterior distribution to answer our research question. One of these quantities is the posterior mean. For any beta distribution, it can be calculated as a function of its two parameters. In this case, the posterior mean is also 88%. The Bayesian equivalent of a confidence interval is a credible interval. Credible intervals take the posterior distribution and give the central interval such that the area between the two values is some given probability. In this case, the 95% credible interval is between 86 and 89.9%. That is, after seeing the reviews, the probability that the true pi is between 86 and 89.9 is 95%. In a similar way, we can use the posterior distribution to figure out the probability that pi is greater than 85%. According to R, it's 99.8%, so I can be pretty sure this cafe would be a good place to go after seeing people's reviews about it. Frequentist methods don't have a direct analog to this probability, but some people have argued that the bootstrap can produce something close to it. If you've been keeping track so far, you may have noticed something. The Frequentist and Bayesian results are essentially the same, but they have radically different interpretations. To Frequentists, 88% is the proportion that maximizes the likelihood of the data we saw, but to the Bayesians, it's the value of pi that maximizes the posterior distribution. The Frequentist confidence interval will contain the true value of pi in 95% of the confidence intervals, while the credible interval tells me that this value of pi is concentrated between these two values. In both analyses, the data suggests that I should go to Mosher because it satisfies my rule. In my opinion, it's easier to interpret the Bayesian results. Once you start to accept that probability can be something other than frequency, it gets easier. You might wonder if it's a coincidence that the two methods produce similar results. You might be surprised to hear, but it's not. It's not just the frequentists who have asymptotic theorems, the Bayesians do as well. This scary expression here is known as the Bernstein-von Mises theorem. I'm not going to explain this expression fully, but I'll just give you the basics. This portion here is the Bayesian posterior, while this term represents the distribution for the maximum likelihood estimator, a popular frequentist method. This entire term represents a sort of distance between two functions. You can view it as the distance between the Bayesian method and the frequentist method. On the right-hand side, you can see that this distance will go to 0. So when the Bernstein-von Mises theorem applies, the Bayesian and frequentist methods will essentially produce the same results. Before I wrap up this video, there's one last thing I want to address. One type of comment I received a lot on my Bayesian statistics video was this notion that you could use Bayesian analyses to concoct any result you wanted. I think it's really funny when people say this, but I've seen it enough that I should address it. On a very surface level, these comments are right. Instead of choosing an uninformative prior like I did in my analysis, I could choose an informative prior. Let's say that I have a heavy prejudice against cafes in this area. Before even trying them out, I'm convinced that their coffee will be terrible. With such heavy prejudice, the parameters for my informative prior will look very different from my uninformative one. If I run the analysis with this prior, then I would get very different results from my original analyses and the frequentist analysis. And the sole reason for this would be because my prior has so much more influence on the posterior. But here's the thing. With Bayesian analyses, you cannot just report your posterior distribution. What my commenters are missing is that you need to report your priors if you want to be thorough. If someone saw my analysis and was surprised, someone can check my prior and question if it's appropriate, If the only reason my prior looks like this is because I have personal prejudice, then it casts doubt on the usefulness of my analysis. Statistics is inherently collaborative, so these concocted analyses don't get very far. You can have strange priors, but you're going to need to justify them with evidence or be forced to redo your analysis. I hope this video has helped clarify the basic frequentist and Bayesian approaches to statistical inference. The truth behind the biggest beef in statistics is that for anybody who actually deals with statistics on an everyday basis, there is no beef. If you want a job as a statistician, then it's in your best interest to be familiar with both and not being an annoying dogmatist. I'm thankful that some people recognize this in my comments, so shout out to those that did. If you like this video, then consider subscribing to the channel. I try to put out new videos every 2 weeks on statistics. You can also subscribe to my newsletter to get my videos straight to your inbox. There, you'll get some extra content on what goes on behind the scenes of this channel. Thanks for watching. I'll see you in the next one.